In this video, I'm going to show you how you can do an analysis of factorial experiments in JMP. So I'm going to do this with the carbon monoxide data set that we had in the lecture. So we'll start with looking at a graphical visualization of this data set. So I might want to look at how carbon monoxide changes as we change the level of ethanol. So right now, this is just plotting the raw data, and we get some idea of what the variation is at each level of ethanol. So the variation here is much larger than the variation down here, and we hope that that can be explained by the different levels of air fuel. And so if I take air fuel and drag it to overlay, we can see that these points up here were due to air fuel 14, these to air fuel 15, and these to air fuel 16. And so if I want to get an idea of the overall relationship of ethanol, I'm going to add this smoother line right here. And we can see that there are significant interactions between ethanol and air fuel. If there weren't any, then these three lines would all look very similar, but they look very different. So 14 is very sharp and very linear, while the other two are roughly quadratic and they're not much of a linear effect. There really isn't much change right here. So one thing I might want to do to simplify this is to, rather than plot the individual points, although this is a good way to check to make sure that you have equal variance at all your levels, change the summary statistic to the mean. And this will give you kind of that nice overall relationship. If you want to make your lines a little bit bigger, I should probably go over this. You can right click, go to graph, and then line width scale, and maybe change that to 30, and it makes your lines a little bit thicker if you wanted to do that. Okay, so we're suspecting that there are some differences between air fuel and ethanol and that there might be potential interactions. So we should do our usual analysis to kind of get an estimate of all those things. So I'm going to go to Analyze and then Fit Model. And the way you type this into Fit Model is very similar to how you do the analysis of covariance with interaction, but now I just have both categorical variables instead of one categorical and one quantitative. So I'm going to highlight both ethanol and air fuel by holding down the Shift key, go to Macro, and do Full Factorial as a straightforward way to add all the effects I'm interested in. I'm going to change this to Minimal Report just because that's what I'm more comfortable with. And we get this output. So this is my estimate of mean squared error, this is my mean squared error, my estimate of sigma squared, 5.167. This is an overall test comparing a full model to an intercept-only model, so something is significant. So we go down to the effect tests, and I want to look immediately at the interactions to see if I can have a good interpretation of main effects. So there is a significant interaction, meaning that we should do an in-depth analysis of my interaction contrast to see which interactions are significant. And so the way we do that is by going to Effect Details. So just for completeness, I'm going to show you how you can do a main effect estimate for ethanol and kind of give you an idea of how JMP can be a little bit picky, and we'll need to adjust that with the interaction contrasts. So if I want to do my two main effect contrasts for ethanol, I can do it right here, and I go to Ellis means contrast. Got to scroll back down. So the one thing that JMP requires when you do these contrasts, I'm not sure if I mentioned it previously, is all the positive coefficients have to add up to 1 and all the negative coefficients have to add up to 1. So for my linear main effect, I'm comparing the low level to the high level. And so that's a 1 and that's a -1, so that satisfies that requirement. Now the way I defined it in the slides is technically this should be 1/2 and this should be -1/2 because we did a divisor of 2. So there's really no way to get JMP to do that with the contrast menu. It has to be all positive coefficients add up to 1 and all negative coefficients add up to 1. So our estimate isn't going to be on the same scale as how I defined the linear main effect. However, the test is going to be the same because the test always adjusts for what the scaling factor is. So this is my linear main effect, and my quadratic has these two positive and the middle one negative. So this is actually the correct scaling for the quadratic effect, because it's supposed to be 1 minus 2, 1 divided by 2, and that gives me 0.5, 0.5, and -1. So this is actually the correct scaling. So those are my two main effects for ethanol. I click done. I know I did this correctly because the sums of squares here equals the sums of squares up there. So the test should be equivalent. But I can go down to test detail and look at the individual estimates for my two effects. So this is minus 4.5, which is what we calculated by hand. We got minus 4.5 here also, but that's because we didn't divide these by 1/2. So if I just divide this by 1/2, I get the estimate that I want. The tests, though, are still not dependent on scale, so that's fine. And we get the test for the linear effect is 0.001. The test for the quadratic is 0.003. Most of the sums of squares looks to be towards the linear effect and some towards the quadratic effect. But again, we're skeptical of this because of the fact that we had an interaction. So we're not going to be totally certain in saying that there's an overall linear and an overall quadratic effect. The linear effect may be highly influenced by air fuel 14, while the linear effect for the other two air fuel settings didn't look to be that significant for ethanol. So I'm just going to minimize this. And now we're going to look at constructing those interaction contrasts. So remember, there's 4 of those things because that's how many degrees of freedom I have right here. There's 4 of those things, so I need to construct 4 orthogonal contrasts. But I have to do this under the requirement that the positive coefficients add up to 1 and the negative coefficients add up to 1. So you have to kind of do some side math if you want to do this in JMP to make sure you're doing this correctly. So the easiest way to do this is to try to create a table like this and to keep track of your coefficients. So technically this is how the interactions are defined in the lecture notes. We're going to have to temporarily ignore the 1/2 or the division by 2 because of how JMP requires the coefficients add up to 1 and minus 1. So I'm just going to look at the numerators of these 4 expressions in terms of the tau parameters and then make sure those coefficients add up. So if you look at the taus involved in AL0 and AL2, you get this top line right here. So AL0 is going to be comparing the first level of A to the second level of A with B held at 0. So B at 0, that's our second index. So this is 0 and this is 0. And so it's 0 minus 2. So this is where I get my 1 and negative 1. AL2 is going to be comparing 0 and 2 with the second index at 2. But it's going to flip the sign because of the negative sign out front. So AL2 is technically 1 minus 1, but when I put the negative out front, it flips those signs, and this is why this becomes a negative 1 and this becomes a positive 1. Notice also that this is the same thing as comparing the linear effect of B at the 0th level of A and comparing that to the linear effect of B at the third level of A. So that's actually an easier way to think about it when you're writing these contrasts. So it starts out fairly simple until you get down to the A quadratic, B quadratic. It does get a little bit more complicated, but if you look at any one of these settings, so if you group these by 3, 3, and 3, you do see some structure and how these are being constructed. So this is what the numerators of all these 4 expressions are going to look like, but in order for this to look like what we need in JMP, I need all the positive coefficients in each of these to add up to 1 and all the negative coefficients to add up to negative 1. So for example, I have a 1 and a 1, so I need to divide these by 2 to get them to add up to 1. And the same thing for the other ones. The last one, I'll just jump right to it, is the more complicated one. So I have 1 plus 1 plus 4 plus 1 plus 1, that's going to give me 8. So I'm going to have a divisor of 8 in some of these cases. So this should be 1/8, this should be 1/8, this is going to be 1/2, 4 divided by 8, this is going to be 1/8, and that's going to be 1/8. And so I have to convert those to decimals because that's how it's going to be shown in JMP. And this is what you end up getting. And this is how it should look. So 0.125, that's 1/8, 1/8, 1/2, 1/8, and 1/8. And you can check to make sure that this is what these values should be. This is just one drawback of JMP, is you have to be able to convert contrast to look like this if you want to do customized contrasts. So I'm going to show you how you can do this in JMP. And the last one is really not so straightforward how you get it to work, but I will show you how you can get it. So let's construct these 4 contrasts, and let's make sure that we can look at our table the whole time while we're doing it. So let me try to see that the best we can. So that's the best I can do in terms of this window. So I want to do the A linear, B linear. I want this to be 0.5, this to be minus 0.5, this one to be minus 0.5, and this one to be plus 0.5. So I'm going to do plus, minus, and then minus, plus. And so here I get 0.5, minus 0.5, minus 0.5, and then plus 0.5. So that's the A linear, B linear. The next one is not too bad either. So I'm going to do, this is the A linear, B quadratic. So I'll do the linear for the first one, the linear for the last one, and they're both pluses, plus, minus, and then I'll do the middle one. So I'll do minus and then plus. So notice I'm not getting the coefficients that I want. What I need to do is put more weight in the middle than the outside. So I'm going to do minus again and then plus again. And that's how I get the correct coefficient values. It's because the middle value needs to be multiplied by 2 compared to the outside pieces. So that's A linear, B quadratic. Now let's do the next one where I do the quadratic up here compared to the quadratic down there. So the quadratic up here is plus, minus, plus. And then let me do it again down here, but I flip it. So now it's minus, plus, minus. And again, I'm not getting the right coefficients because I need to do the middle one twice. So I'll do that minus and that plus. And so that's just how I'm getting the correct weighting for the coefficient values. And then the next one, A quadratic, B quadratic, I just need to do the quadratic for each individual piece, and then I'm going to have to add more weight to the middle pieces. So plus, minus, plus. Let me add this. Now you can't add any more because it's all added up to 1. So, and then let me do it for the bottom one. This is also plus, minus, plus. Let me add one more to that. Okay. And then I need to do the middle level. I'm going to do minus, plus, minus. And so this is not anywhere close to being correct. And then the way I'm going to fix it is I'm going to add more weight to the very middle level because right now it's just 0.2. I need that to be 0.5. So I'll add a plus there and a plus again and then a plus one more time. And this is how I get the correct coefficients. So there's a couple different ways that you could get that, but that was the easiest way that I was able to get it. So this is kind of a pain in JMP to do correct, to get the contrast correct. So that's why it's important that you can create this table yourself to make sure that you have the right coefficient values. And let's click done. I know I did this correctly because I have 678 and then 678 right there. Let me get down to my test details. Again, these coefficient values are pretty much way off compared to what they're supposed to be down here. I believe it's correct for this one, but probably not for any of the other ones. So you'll just need to keep in mind the scaling effect on some of these estimates. And so what we want to look at is what the individual tests are for each of these sums of squares. And that's going to tell us which interactions are going to be important and which ones aren't. So if you look down at these sums of squares, we're kind of getting an idea of the relative importance of all these different linear effects, or all these different effects inside that overall interaction test. So our total sums of squares here is 678 for the interaction effect. And almost all of them are coming from the A linear by B linear effect. And the other sums of squares are relatively small. So that p-value is insignificant, this one's insignificant, this one's maybe borderline significant, but it looks like for the most part that the main thing that's driving this two-way interaction is the A linear by B linear. So if there's no quadratic effect that's important here, it's actually okay then for us to interpret overall quadratic effects because the quadratic effect isn't interacting with anything else. So in fact, the estimate of the quadratic effect up here, that would be a valid main effect interpretation because it doesn't interact with anything. The linear effect, however, does make huge differences. And so if we ever wanted to talk about linear effects, we have to do it at a level by level comparison. So if I wanted to look at the linear effect for air fuel 14, I'm going to go back up here. So the linear effect for ethanol at air fuel 14 is I want to compare maybe let's do it the other direction. Let's compare the high level of ethanol to the low level of ethanol at air fuel 14. And that has a huge sums of squares. The estimate is 28. So this is the linear effect as I go from the high level of ethanol to the low level of ethanol at air fuel 14. And so if I try to do the same comparison, let's say, but at level 15, and let me do it also at level 16. So high level 16, low level 16. And I go to test detail, both of them appear to be significant, but not nearly as significant as it was up here. So notice this estimate's 28, but this is only 7 and minus 8. So they're much lower magnitude than what we have up here. And this is the whole reason why we have an A linear by B linear, B linear interaction. If there was no interaction, these estimates should all be roughly the same, but we can see that they are pretty different from each other. So that's how you do this in JMP. The contrasts aren't necessarily straightforward, but you'll see in the SAS video, it's much easier to construct customized contrasts in SAS than it is in JMP.